Hey there, and welcome! Have you ever actually stopped to think about the simple genius behind something like a bottle opener? Or how you can lift a super heavy load in a wheelbarrow with like one hand? Well, these are levers, and they are literally everywhere, making our lives easier in some pretty fascinating ways. So today, we're going to break down the hidden physics that give these simple tools their surprising power.
Yeah, that's the big question, isn't it? It almost feels like magic, but I promise you it's pure, unadulterated physics. These tools don't just help us, they can multiply our strength or even our speed. And we're about to dig into exactly how they pull it off. So, the key to understanding any of this is a concept called mechanical advantage. You can really think of it as the secret sauce, the special ingredient that gives simple machines all their power. In the simplest terms, mechanical advantage is just a measure of how much a tool is amplifying your force. It's a comparison, really, a ratio of the force you get out of the machine to the force you put in. Basically, it answers the question, how much bang are you getting for your buck? And here is the key idea, the part that matters most. When that mechanical advantage number is greater than 1, it means you're getting a real force multiplying benefit. You put in a little bit of effort and bam, you get a whole lot more force out the other end. This is where the magic really happens. So, with that in mind, let's start with the classic force multiplier, the second-class lever. This is the type of lever that makes you feel, and literally be, stronger. The defining feature here is incredibly simple. The thing you're trying to move, that's the load, is always positioned somewhere between your effort and the pivot point, which we call the fulcrum. And this specific layout is exactly what guarantees you a force advantage. Why? Because you apply your effort farther away from the fulcrum than the load is. That extra distance gives you more leverage, letting you generate a lot more turning force with less actual effort. Your input gets magnified, which is why a second-class lever always has a mechanical advantage greater than 1. And you use these all the time, probably without even thinking about it. A wheelbarrow, right? The wheel is the fulcrum, the load is in the middle. A bottle opener, prying off a cap. A nutcracker. Even a simple door. The hinge is the fulcrum, and you push on the side farthest from it to make it easy to open. They all make you stronger.
Okay, so now let's switch gears. We're going to move from force multipliers to something completely different, but just as useful, the third-class lever. You notice the switch? With third-class levers, the whole arrangement just flips. Now, your effort is the thing being applied between the fulcrum and the load, and trust me, this changes everything. And this is the part that sounds kind of backwards, right? With this setup, you actually have to put in more force than the load you're trying to move. Its mechanical advantage is always less than 1. You're actually at a force disadvantage. Which leads to a really good question, doesn't it? If this lever makes you work harder from a pure force perspective, what on earth is the point? Why would evolution or engineering ever come up with this design? And here is the brilliant trade-off. What you lose in force, you gain back big time in range of motion and speed. A small, short movement where you apply the effort results in a much larger, much faster movement at the end where the load is. Just think about it. When you cast a fishing rod, your hand only moves a little bit, but the tip of that rod just whips through this huge arc. It's the same with a hockey stick, a shovel, or even tweezers. And you know the best example of all? Your own arm. Your bicep, that's the effort, pulls up near your elbow, the fulcrum, which lets your hand, the load, move super quickly over a long distance. Okay, so we've covered the force multiplier and the speed multiplier. Now let's tie it all together with a super simple trick so you can remember which is which forever. Now, to complete the picture, let's just quickly bring back the first-class lever. This is your classic seesaw or a pair of scissors. It's the one where the pivot point, the fulcrum, is in the middle. This one can multiply force or not. It all just depends on where everything is placed.
And it all comes down to this one simple trick, the FLE rule. To identify any lever, you just have to look at what's in the middle. For a first-class lever, the fulcrum is in the middle. For a second-class lever, the load is in the middle. And for a third-class lever, the effort is in the middle. FLE. 1, 2, 3. It's as simple as that.
So let's leave you with a final thought to put this new little tool to use. Think about how you use a shovel. Your top hand acts as the fulcrum, right? Your bottom hand provides the effort right there in the middle, and the dirt at the end is the load. So using that FLE rule, what class is it? Think about it. This simple physics is all around you, hiding in plain sight.